Hello, ladies and gentlemen. First of all, let me thank you for all of you for coming here today. And let me start by saying a few words about my own background. As you can see on the screen, our topic today is quantum mechanics and linear transformation preserving orthogonality in Crane spaces. Uh, my name is Sisilia Sylviani and I'm from Department of Mathematics, Universitas Pajajaran. My field research is algebra and its application to other fields. So let's start the presentation. Wiener's theorem on symmetry transformations plays a fundamental role in quantum mechanics. It states that any quantum mechanical invariance transformation, or we can say symmetry transformation, can be represented by a unitary or anti-unitary operator on a complex Hilbert space, and that, conversely, any operator of that kind represents an invariance transformation. Or in mathematical language, the results can be reformulated in the following way. If H is a complex Hilbert space and T is a bijective transformation on the set of all one-dimensional linear subspaces of H, which preserve the angle between every pair of such subspaces, in the terminology of quantum mechanics, this angle called a transition probability, then T is induced by either a unitary or an anti-unitary operator U on Hilbert space H. Your generalized this result by requiring only that T preserves the orthogonality between the one-dimensional subspaces of H. So, in this case, we see that the preserving properties of the transformation between one-dimensional subspaces of H is playing an important role. Moreover, indefinite inner product spaces are even more useful than definite ones in describing several physical problems. In the last decades, it has become quite clear that indefinite inner product space is more and more useful than definite ones, especially in describing several physical problems. This has raised the need to study Wiener's theorem in the indefinite setting as well. For example, as a solution of the divergence problem in quantum field theory and as a method to obtain better regularity properties for theories previously regarded as untractable. An indefinite metric is not only a promising suggestion but an avoidable feature if one wants to preserve some basic properties of the fields like relativistic covariance and locality. In this presentation, I will uh, focus on one of the example of indefinite inner product space, which is Crane space, and I will explain what is Crane space in the uh, next slide. This this result is a development of the result obtained by Szymanski, which is about linear mapping the approximation orthogonality in a inner product space. This is the result. The theorem said that if X and Y be two inner product spaces over a complex field, for non-zero mapping from X to Y, these statements are equivalent. First, that norm of Tx is equal to gamma x, and then T is an isometry, T is linear and strongly orthogonally preserving, and T is linear and orthogonally preserving. And in this presentation, I will discuss the development of this theorem for Crane spaces. I will not discuss about its usage of the quantum mechanics. I'm just going to focus on the development of this theorem, this specific properties of um, mapping from Crane spaces. First, I'm gonna explain some terms and definitions. Let V be a vector space over complex space C. A function bracket from V cross V is indefinite in a product space on V if the following condition apply. First, linearity on the first argument, and symmetry, and non-degenerate. Next, an indefinite inner product space K with indefinite inner product bracket is a Crane space if K can be written as orthogonal direct sums of or as we can see here is K is equal to K plus or plus K minus, where K plus and K minus are Hilbert spaces. And let X and Y be two Crane space. Mapping T from X to Y is orthogonally preserving for all xy in X. If X orthogonal Y, then Tx orthogonal Ty. And called strongly orthogonally preserving is the condition applied in both ways. This is I'm gonna skip this. This is the properties that we we uh, we have in Crane spaces. It is the development from inner product spaces to Crane space. This is also one properties. This is the fourth. So those properties, those lemma 1, lemma 2, lemma 3, and lemma 4 is used to prove that the properties that Sylviani present or Sylviani have is also can be applicable when the space x and y is a Crane space, which is in an indefinite inner product space. So we see here that the properties is applicable to Crane space, but with a little bit adjustment in this point. We add the condition where the indefinite inner product uh, of x to itself it's not equal to 0, and in the indefinite inner product from tx to itself is not equal to 0. So this is the end of my presentation. This is the properties that we can use. We can use in Crane space related to uh, preserving properties that also can be used in order to help solving problems in quantum mechanics. Thank you all for your attention. Uh, this is it. I guess for me this is my uh, references. Thank you and have a good day.